Graph Theory Class 6, Video 1. In this video we're going to try and classify some simple graphs. Classifying things is something which mathematicians try to do a lot. The general philosophy behind it is mathematicians would define some family of objects. So in this case that's graphs. And now that we've got that definition, we want to know how many graphs are there. How many graphs are there that satisfy this certain property or that certain property. You know, we want to count how many graphs there are and nicely compartmentalize them and organize them, and it makes us feel secure. So let's try and begin. The first thing you'll realize is it's impossible to classify all graphs because I could just keep making them more and more complex, right? If I just have some vertices, I can always just keep adding more and more and more edges or some loop edges. I can just keep making them more and more complex. So even if I restrict myself to just having 4 vertices, there are still infinitely many different types of graph because I can just keep adding more and more edges, forever and ever and ever. So there are infinitely many graphs on 4 vertices. Well, this is disappointing and unsatisfying. So instead of trying to classify all graphs on 4 vertices, mathematicians restrict to saying, I just want to classify simple graphs instead. And I'll remind you that a simple graph, what does this mean? This means it's undirected, unweighted, not a multigraph, and not a loop graph. This is a simple graph, okay? So for example, this graph I drew right here is not simple because it has some loops like here, and it has multi-edges here. So this is not a simple graph. Okay, so let's try and classify simple graphs. Example. Classify all simple graphs with 3 vertices up to isomorphism. So what I mean by up to isomorphism is if 2 graphs are isomorphic, I count them as the same. Okay? Because if I don't count up to isomorphism, well then you're essentially counting infinitely many different ways of drawing the same graph. So if they're isomorphic, I count them as the same. And this is a very important caveat. So 3 vertices. The first thing I'm going to do is draw 3 vertices. Okay, and this is a simple graph. There are no edges, but that's okay. I never said my graph had to have edges. I never said a simple graph had to be connected. I just said it has to be undirected, unweighted, not a multigraph, and not a loop graph. So this satisfies all of them. So that's my first simple graph with 3 edges. Now let's try and be methodical. This might sound a bit abstract, but is there another graph with no edges and 3 vertices? Well, if you think about it, there's not, right? There's only one graph on 3 vertices that has no edges. Now let's move on to graphs with 1 edge. So I'm going to put an edge right there. Okay? So that's my second graph. I'll try and draw another graph. You might try and draw something like this. But if you actually think about this, this graph and this graph are isomorphic. They're isomorphic. I could label them like A, B, C, C, A, B. And that's a labeling which demonstrates that they're isomorphic. So that means that I shouldn't count this graph as a new graph. But if I add another edge like that, then now it's a new graph. Now it's not the same as any of the previous graphs. Okay? And if you think about it, this is the only graph on 3 vertices with 1 edge. Yeah, and similarly, if you think about it, this is the only graph on 3 vertices with 2 edges. So the next number of edges is going to be 3, and I don't really have a choice on how I do this. I have to do it like that, okay? And this is the only graph on 3 vertices with 3 edges. And now if you think about it, that's it. That I can't make another simple graph which isn't already in my list, right? Because you're not allowed to do something like this, because this is not a simple graph. This is a multi-graph now. So these 4 graphs right here are a complete list of all the simple graphs on 3 vertices. Okay? And that's the end of this example, and that's the end of this video.